Welcome to the lecture series on database management systems. In this lecture, we talk about entity relationship modeling. To build any database, we need a model to understand how does it look like and what is the information that is to be stored and what are the operations that we need to perform on the database. To understand the scenario, the first step is requirement analysis. In this phase, the developers and the customer who wants the database to be built need to sit together and understand each other's requirements. As a developer, the coding part and the technicalities may be known, but from the customer end, the requirements of the customer and the domain knowledge of the problem or the area on which the database is being built is not known to the developer. So they need to understand each other very well. The customer do not know the technicalities and the technical persons do not know the requirements of the customer fully. So in this phase, they need to sit together and understand intricate details of each of the data values that are to be stored in the database. Once something goes wrong at this stage, will spoil the entire database design, because after design of the database, if the customer says some other requirements which are missing, then sometimes we may have to build from the scratch again. So this requirement analysis is a very crucial phase. Once that requirement analysis is done, then the logical design of the database has to be done. Logically, how the data flows, how the data is stored, how the data flows, and what are the linkages among the data items is to be established in the logical design. Once this is satisfactorily done, after thorough verification, the physical actual database is to be built. Once coding part is done, once it is built, after thorough testing, it has to be implemented for beta testing with dummy data or pseudo data, and then it has to be deployed. Once it is deployed, the monitoring phase will start. Continuously will monitor the performance of the database for some few months or days, and then fine-tuning can be done if required according to the customer's needs. This is how we need to go into the database design. To create a logical design of the database, we need to have some graphical representation or visual representation is more suitable for the design of the database. The entire database will consist of entities, attributes, and relationships. Entities are objects with distinct characteristics or independent existence. They are called objects. Every object will have attributes or qualities, and the collection of attributes will define the entity. Given a set of entities, there may be a relation. We can establish a relationship with another entity set, and entire database can be seen as a relationship among entity sets. We need to establish the exact relationship or feasible relationship existing between the entity sets. The entire database design, the logical design, boils down to design of the identification of the relationships and design of the relationships among the entity sets suitably in such a way that whenever data is required, we need to able to combine the entity sets through the relationship and extract the required data. To establish the entity relationship diagram, let us understand some of the basics of ER diagrams. We'll represent entity with a rectangular box and attributes or qualities of the entity with a oval shape. And whenever there is a relationship among the entity sets, we represent with a diamond. And among the entities, a weak entity set is one special case that is represented with a double box. Similarly, when it comes to the attributes, multi-valued attributes are represented with a double oval, and weak relationship can be a weak relationship also, that is represented with a double diamond. At the end of requirement analysis phase, we should have a clear-cut understanding on the collection of entity sets and attributes of each of the entity sets. When it comes to the attributes, there are types of attributes are there, and we should have a clear-cut representation of these attributes. To start with, we'll have a simple attributes which are indivisible and atomic. They cannot be divided further. And the collection of attributes are represented in the form of ovals, and all the attributes of entity sets are connected with a rectangle from the oval through lines. When it comes to the derived attributes, an attribute may not have the independent existence, and it may be computed with respect to another attribute. So for example, here date of birth is an independent one and a fixed one, once for all is fixed, whereas age is varying with respect to time and it depends on date of birth. So in such cases, we take date of birth as the original attribute, and if at all age has to be stored, usually we don't take age as an attribute. If at all any requirement is there to store the age also, then it has to be computed based on the date of birth and then stored here. So it has to be updated periodically. So then age becomes a derived attribute. The derived attribute is represented in the form of a dotted oval for representation. Similarly, some of the attributes may be composite attributes. Attribute itself have several components. Say for example, address. Address may still have several components in it, like street or flat number and city and country, like that. So how do we store the address is an issue here. At what level you want to have the granularity depends on the requirements. In the requirement analysis, if you know that we need to store the individual parts of the address, we should be able to access them, then we need to represent it in the form of a composite attribute. If we are not bothered about the individual components, we can store the entire address as a string, and that's it. A simple attribute can be stored as an address. It all depends on the requirement. So in this case, address is a composite, can be treated as a composite attribute. Similarly, name can also be treated as a composite attribute if we take first name, middle name and last name. Sometimes certain attributes may have multiple values to be stored. Say for example, cell number. If multiple cell numbers are to be stored for a particular person or a particular object, then we can do it in two ways. One, we can store each of the cell number as an attribute, like primary cell number or secondary cell number, like that. Or we have an option to store multiple cell numbers as a single value of the attribute. Generally, we don't do that. We don't encourage such kind of scenarios unless the situation demands. The drawback of storing such a scenario is that while processing the queries, if we retrieve the cell number, it is hard to separate these two cell numbers through a query. But that possibility is there. Such a attribute is called multi-valued attribute. And the multi-valued attributes are denoted by double oval. Now, another key scenario is key attributes. Some of the attributes are such that they uniquely identify the objects from the entity set. Such attributes are called key attributes, and we know the primary key constraints, and such primary keys are keys denoted with the underline in ER diagrams. After identifying the entity sets and attributes of the entity sets, the next step will be to establish the relationship, identify the relationship between the entity sets and establish the relationship. There are several possibilities of relations. The primary is binary relation, where relationship exists between a pair of entity sets. Sometimes the relationship may exist between three entity sets simultaneously, or three entity sets involved in a single relationship. Such a relation is called ternary relation. Similarly, if four entity sets are related in a single relation, it is a quaternary relation. In general, if there are n number of entity sets directly involved in a single relation, it becomes an n-ary relation. So depending on the scenario or the situation, we need to establish such kind of relationships. In this case, we are trying to establish enrollment as a relationship between student and courses, where every student may involve with a course through enrollment. Similarly, every course may have students enrolled into it. Similarly, in case of ternary relationship, here registration is taken as a a relationship between student, courses, and faculty. So this provides a flexibility here. Some of the students may be registered with a course at a particular faculty. Similarly, a faculty have students with respect to through the registration for some of the courses he is offering. So faculty may offer different courses, students may register different courses. So there is a ternary relationship exists between students, courses, and faculty. Sometimes we may require to represent a relationship from a set onto itself, where some of the objects are related to some of the objects in certain way, and those objects are related to another set of objects in the same set in different way. So for example, in the case of employees, reporting is one issue here. So he is superior to whom? An employee can be viewed in two ways, because he is superior to someone else, and he is someone else is superior to him. So such kind of relationship has to be established among the employees in the same set. Otherwise, if it has to be represented in the form of two objects, then duplication may arise. So such type of relations are called recursive relations. And in case of relationships, sometimes one object in one entity set may be related to n number of objects in the other set or entity set. They are called types of relations are there: one-to-one, one-to-many, many-to-one, many-to-many. All such kinds of relations can also be represented in the form of ER diagram. Here are some alternative representations of one-to-many or many-to-many relationships. If one-to-many is there, on the right hand side, multiple divisions can be represented. Many-to-one, the left hand side divisions are there. One or more. So minimum one is mandatory. In such case, left side division is there and arrow, single line is there. So one and only one are mandatory, but minimum mandatory is there. So two lines are depicted here. Zero or more, so optionality is there. In such case, a circle and a line. Like this, we can have different types of relations. In the relationship, there are two types of participations. One is total participation, another is partial participation. In the total participation, every element in one entity set should participate in the relationship with at least one element in the other set. Whereas in case of partial participation, some of the entities may not participate in the relationship at all, or some of them may relationship exists. So such kind of relationships can also be depicted here, and there is a double line. It's indication that in the connection, it's an indication that it's a total participation. In some cases, collection of entities may have subclasses among them. The overall collection will have certain attributes, and the subclass will have the special properties apart from the regular ones for the overall collection. In such case, we'll use easy relationship. As an example, if we take students as a general collection of entity sets, say roll number and name are the common attributes for all the students. But among the students, two groups are there. Subgroups are there. One is postgraduate collection and undergraduate collection. So for postgraduate collection, apart from roll number and name, supervisor is another attribute. Whereas for undergraduate students, some other attribute may be there, like CGPA or some points. So this EZA represents the specialization of students into two groups. Such kind of specializations can be represented to any extent, any depth as per the requirement. From bottom up, it can be seen as generalization. From top to bottom, it can be seen as specialization. Another scenario is called aggregation, where the relationship has to be established not directly with the entity set, any particular entity set, but with another relationship. So, for example, in this case, a relationship is there connecting three entity sets, but we need to establish a relationship with another entity set which is governing the entire scenario of the relationship among the three entities. In such case, we'll use a box to indicate the aggregation of the entire collection there, and that entire collection is related with another entity set in the form of a relationship. So for example, a manager manages a project. The project may have individual entity sets and attributes among themselves and relationship among themselves, but the manager will manage not only one particular entity set among the group, but he manages the entire scenario. To represent this, we'll have a box and relationship with another entity. Some of the scenarios we have seen, the detailed analysis and detailed representation requires a lot of patience and time. Now, while giving the names to the relationships and names to the attributes, names to the entity sets, this should be suggestive and domain specific. By looking at the attributes, names of the attributes, and looking at the understanding the relationship among the attributes or entity sets, the naming should be very crisp and precise. So use apt names for the relationships, attributes, and entity sets. As far as possible, use singular nouns for entities. Adjectives may be used to distinguish entities belonging to the same class. Similarly, attribute names should be meaningful, unique, system independent, and easily understandable. And there should not be any vagueness, there should not be any uncertainty in the relationships or the data representations. And directly do not connect a relationship with another relationship, but we can connect a relationship with an aggregation with respect to the already existing relationship among a collection of entity sets. So these are some of the issues to represent the ER diagrams.